Hi everyone, welcome to another amazing class on monsoons. Today, our speaker is Dr. Vasu Misra. He's a professor of meteorology in the Department of Earth, Ocean, and Atmospheric Science and the Center of Oceanic Atmospheric Prediction Studies at Florida State University. His research interests are in tropical meteorology and climate modeling, which has led to studies in monsoons, tropical ocean variability, easterly waves, and tropical cyclones. He is also involved in climate application studies in hydrology and regional and urban planning. And Vasu is a member of our working group of American monsoons. Vasu takes a lot to stay connected with us, and I will share my screen and you can start your presentation.
Sure.
Is it okay?
Yes, perfect.
Okay, I'm here.
Thank you. Good morning, everyone. It is a great pleasure to speak in this forum, and I hope I am audible to all of you. Today, I'm going to be talking about the Central American monsoon. Next slide, thank you. And this is a very telling picture of the domain of the Central American monsoon. Around 15° north is where it separates between the North American and the Central American monsoon. So it cuts through middle of the isthmus connecting the two continents, the South American and the North American continent. There's a distinct signature of the Central American monsoon that I'll be talking about later, which is called the midsummer drought. There is a dip in the rainfall in the middle of the summer with a biannual peak on either side in June. There is a peak, and then July, August, there is a dip, and then again in September, it picks up again. But as you move towards the equator, the phenomenon of the midsummer drought disappears. Next slide, please. So Central America is just about 0.5% of the Earth's terrain, but contains 7% of its flora and fauna. It is considered a biodiversity hotspot and a center of nature conservation. Next slide.
A second. Oh.
Sure. It is also very rich in agricultural production. It is one of the biggest coffee producers and exporters. Agriculture is a large component of the economy of the Central America, and therefore they are critically dependent on the forecasts at the seasonal scales. They are also a source of great hydroelectric generation, and obviously that also warrants a seasonal forecast with some amount of accuracy for them to plan. Tourism is also huge. The tourism season is during the dry season, and obviously they also are dependent on useful seasonal forecasts for the region. Next slide, please. These are some pictures of the tourism spots. So go ahead, next slide. Okay. So the isthmus, which is basically a strip of land connecting two continents, from Guatemala and Belize in the northwest to Panama in the southeast, the isthmus ranges in width between 100 to 400 kilometers, with a length of around 1,600 kilometers, all the way from Panama to Guatemala. Continental divide, there are mountain ranges. There is Sierra Madre on the north side, and the mountains below are two separate mountain ranges. They divide Central America into the Caribbean slope and the Pacific slope, bordered by the Caribbean Sea on the eastern side and the Pacific Ocean in the western side. Next slide, please. So this is a high resolution picture of the mountains over land and the ocean floor, or the bathymetry over the ocean. So you can see the Central Cordillera and the Sierra Madre Mountains that basically divide the Pacific slope and the Caribbean slope, or the Caribbean side of the isthmus. The seasonality of the hydrological cycle, at least on the Pacific side, is critically dependent on the migration of the ITCZ in the Pacific as it traverses south of the equator and north of the equator. We'll talk a bit about tropical easterly waves and monsoon gyre and the low-level jets as the talk proceeds. As I said earlier, we'll also talk about midsummer droughts and diurnal variations. There are also subtropical highs on either side of the ocean basins that we'll be talking about, both in the Pacific as well as in the Atlantic. The important features, as I said, this is one of the most challenging areas of the world for numerical modeling, given the geography, a very narrow strip of land with very steep orography and covered by or with the neighboring oceans that are very active in terms of tropical cyclone activity. Next slide, please. So I'm going to revisit this picture once again, because if you see on the northern side of this picture, the rainfall has got one annual peak sometime in the summer, which corresponds to the North American monsoon. So as you move further up into United States, into New Mexico and Arizona, they seem to have one annual peak. And if you move further into the Caribbean, further east, then the annual cycle actually becomes rather flat. It is raining almost throughout the year in the Caribbean side. But right over the isthmus, you see an annual peak on the northern side. But as you move further south, you can see the biannual peak, which is called the midsummer drought, which is a phenomenon that is unique to this region. And as you move further towards the equator, that bimodal peak disappears. Next slide, please. So this is a picture from NASA's remotely sensed rainfall, which is called iMerge rainfall. It is available at half a degree at half-hourly interval from 1998 to the present. So what we have done here is computed the intensity of the midsummer drought, which is basically the difference in the rainfall in the midsummer versus the biannual peak. So we take the average of the biannual peaks and subtract it from the dip in the middle of the summer that it has. And that amplitude of the midsummer drought can range anywhere from about 5 millimeters per day to about 0.5 millimeter per day. And it is largest on the northern side of the isthmus compared to the southern side. So I'll talk about this dry corridor that that is prevalent in this region, and that's where this midsummer drought is pretty frequent. In terms of seasonal variability, again, in the northern side of this Central American domain, the midsummer drought variability explains almost 50 to 60% of the summer season variations. So that is a large fraction of the summer season rainfall variability is explained by the variability of the midsummer drought. Next slide, please. So as I said, there are two portions of the Central American domain. One is the Caribbean slope, where you have the Central Cordillera bifurcating the Caribbean slope from the Pacific slope, and the Sierra Madre Mountains further up north that bifurcates between the Pacific slope and the rest. So in the Caribbean slope side, there are again two peaks of rainfall, one in the summer and one in the winter time. And both of this corresponds with a similar biannual peak of a low-level jet called the Caribbean low-level jet. So the Caribbean low-level jet serves as a moisture source to Central America, and the Caribbean Sea is a moisture source almost persistently throughout the year, with a bit of a seasonal variation with relation to both the low-level jet as well as a bit of a displacement in the winter time towards the Gulf of Mexico. Next slide, please. On the Pacific side, there is, as I said, the midsummer drought, where again, July and August, there's a dip. June, there is a peak. And again, in September, there is a peak. So this July-August period, when there is a minimum, this difference between the biannual peaks is what is measured as the intensity of the midsummer drought. On the Pacific slope side, the seasonal variability is largely dictated by the meridional migration of the ITCZ. However, the climatology of the Pacific slope is controlled far beyond the ITCZ, because there's variability of the Pacific Ocean sea surface temperatures. There is the upwelling related to the Costa Rican dome that also affects the intensity of the ITCZ and therefore affects the seasonal cycle of rainfall or the hydrological cycle over Central America. Seasonally, in the summer, humidity transport from the Caribbean contributes more to precipitation over Central America, both in the Caribbean slope side as well as the Pacific slope side, compared to the Pacific. So Caribbean moisture source is a dominating moisture source over Central America. Next slide, please. So the Central American dry corridor is shown by this yellow shading over here. That is the relatively drier portion of Central America. It has long dry seasons in boreal winter prone to drought and has a very marked midsummer drought. One of my earliest slides showed the intensity of the midsummer drought, and the midsummer drought is rather intense over these yellow shaded regions, which also has a pretty prolonged and intense dry season in the boreal winter. So the midsummer drought, as I said, is prevalent in July, August, and frequent dry spells during the wet season from May to October. So one has to be very careful in planning for water resources in this region, because they have to sustain during a pretty prolonged dry boreal winter. Next slide, please. So these are the myriad of low-level jets usually found at 925 or 850 or even very close to the surface. And I'll go through each one of them one by one. You have the Caribbean low-level jet, which is out in the open ocean. It has an intensity of about 15 meters per second. And it has a biannual peak that coincides with the biannual peak of rainfall, both in winter and summer. Choco jet is very close to the surface. It is one of the weaker jets. It is westerly, southwesterly, and it appears in summer and fall. And I'll show you cross sections of these jets in the next slide in a moment. Then you have the Papagayo jet, which is again seen at about 925 hectopascals, about 10 meters per second is the core wind speed. It is northeasterly jet of Pacific coast of Nicaragua and Costa Rica in winter and spring. And then Tehuantepec jet, which has a core wind speed of about 8 meters per second. It is a northerly jet in the Gulf of Tehuantepec. Again, appears in winter and spring. And finally, Panama jet, which is approximately 10 meters per second in its core. Again, it's a northerly jet in the Gulf of Panama. And all of this basically is largely because of mountain gaps, which allows the northeasterly trade winds to flow through. On the other hand, the Caribbean low-level jet and the Choco jet are responding to both the SST gradients. And the Caribbean low-level jet is responding to SST gradients between the Atlantic and the Pacific. And also, there has been some studies which claim that the topography over Venezuela has some role to play in creating some barotropic instability in the region. Um, on the other hand, the Choco jet is also responding to some SST gradients, and as a result, you develop a very low level, very close to the surface jet, which is relatively weak compared to the other jets. But the Tehuantepec jet, the Papagayo jet, and the Panama jet are largely owing to the fact that there are gaps in the mountain ranges, which results in the channeling of the winds from one ocean basin to the other. Next slide, please. So if I look at the seasonal cycle, which I had said that some of them, like the Caribbean low-level jet, has a biannual peak in summer and winter. Papagayo jet has again in spring and fall. The Panama jet has got a peak sometime in the early spring and rather flat. The Choco jet is also does not have a very strong seasonal cycle, and the Tehuantepec jet appears in the late fall season. And the cross sections are shown in the next panel here at the various pressure levels. The Choco jet is the one that appears very close to the surface. That is panel I. And the first panel F there is the Caribbean low-level jet. Panel G is the Papagayo jet. Panel H is Panama jet. Panel I is the Choco jet. And panel J is the Tehuantepec jet. And once again, I've put the slides for the previous slide here just to give you a reference of where these jets are. Next slide, please. The Central American gyre is also something very typical to this region. It appears late in the season. There is this low pressure system that is caricatured in this top panel here. And in fact, sometimes it also pushes the tropical cyclones from the East Pacific into the Caribbean side. Or it can also spawn off tropical cyclones from this large scale gyre that develops in the low levels. So the bottom panel is showing you a height map, surface height map, where you can see this monsoon gyre very clearly. It appears late in the season, and if you can go to the next slide. The vertical structure is largely seen, as I said, in the lower troposphere. 925 to 850 hectopascal is strongest and most consistently identifiable cyclonic circulation. Between 700 to 850, it is associated ascent and thermodynamic response, but generally not a closed gyre. And at 200 hectopascals, often an anticyclonic warm core response. These are non-baroclinic gyres, but there are baroclinic gyres that are seen in the winter as well. And those are identified by PV anomalies at 200 hectopascals. The gyre is formed by interaction of convection, land-sea thermal contrast, moisture convergence, and changes in the tropical circulation. So during the gyre development, the easterly trades weaken and the westerly flow develops on the Pacific side. These westerlies can generate cyclonic shear, which is ultimately converted to curvature vorticity, which leads to the development of this gyre. Persistent deep convection of the monsoon in Central America produces substantial latent heating and ascent, lowering the lower tropospheric geopotential height and organizing the cyclonic circulation. And the gyre itself draws moisture from both the Eastern and the Caribbean, producing broad moisture convergence in rainfall, and topography has an important role to play for the generation of this monsoon gyre. Next slide, please. There is also very prominent diurnal variability, and this has been described using, again, the GPM rainfall, which is available both over ocean and land for about 27 or 28 years. And basically, on the left panel, you see the diurnal amplitude, which is pretty significant over the land portions. It ranges anywhere from 6 to 15 millimeters per day, both on the Caribbean side and on the Pacific side. It is also interesting to see on the eastern tropical Pacific, there is very strong diurnal variability of rainfall even on the ocean side. And if you look at the diurnal phase, that is the time at which there is the diurnal peak of rainfall, once again, you see that over the land portion, it is in the late afternoon, local time, 17 to 19 hours between 5 to 7 p.m. But on the Caribbean slope side, you can also see very late in the early in the morning or late in the night, around 1 a.m. is when you see a diurnal peak in rainfall. And on the ocean eastern Pacific side also, you see a similar peak. And so this diurnal phasing and diurnal amplitude is a very important component, and it is somewhat of a mystery in some sense of the reasons why the neighboring oceans peak at a different time than the land surface. There are some theories behind it, but I'm not going to go over it at the moment. Next slide, please. Tropical easterly waves, that's actually a phenomenon that is seen across the global tropics, but it gets particular attention, especially in the Caribbean side as well as on the Eastern Pacific side, because they are responsible for a large fraction of the tropical cyclones that are generated. It appears between 5 north to 25 north and 5 south to 25 south. The waves travel at a speed of about 300 to 500 kilometers per day. They have typically a wavelength of 1500 to 4000 kilometers. They have a period of 2 to 10 days. And a large fraction of Atlantic tropical cyclones and even the Eastern Pacific tropical cyclones have their origins from these waves. Next slide, please. So I'll be talking about the onset of the monsoon and how we diagnose it, but I just wanted to talk about or introduce this concept before I define it, that once we know, we know that the variability, there's variability in the onset of the Central American monsoon. When it starts, when does the monsoon start each year? That date varies from year to year. And on the right side here in figure 2, I'm showing you a scatter plot between CAM onset date in Julian days on the y-axis and May through November ENSO index, which is the ocean Nino index, which is basically Nino 3.4 averaged SST index. And the correlation between the two is 0.18, almost insignificant. The p-value is pretty high, 0.23. So there is barely any relationship between the variability of the onset of the monsoon over Central America. But there is quite a bit of relationship between the onset of the monsoon in Central America versus the seasonal length and seasonal rainfall. Now, there is a small caveat here. The onset date for this particular work that I'm mentioning has been computed, averaged over Panama, Costa Rica, and Nicaragua. I've not used the rest of the countries' onset date. I've just averaged the onset date over Nicaragua, Panama, and Costa Rica to define the onset of the American monsoon, because the latitude band over which these countries reside, that's where you find majority of the tropical easterly waves. If you go further up north, you don't see it. So I'm trying to draw a connection between the tropical easterly waves and the onset of the monsoon. Next slide, please. So this These two tables are very revealing in the sense they are describing the correlations of the basin-wide tropical cyclone metrics for the northern Atlantic Ocean. So these are the named storms with a wind speed of 17 meters per second. The tropical storms with the maximum wind speed of up to 17 meters per second. And it is, the correlation is minus 0.12, and the p-value is pretty large. So barely any significant correlation. The storm days, the total number of storm days is minus 0.21, p-value is 0.19. In contrast, if you do it with the ONI index, it is far more significant. And so, you know, for tropical storms and tropical storm days in the Atlantic side, it is far more strongly correlated with the ENSO variations. But in terms of hurricanes, it starts to become slightly more significant, although ENSO still has an overbearing influence with minus 0.48 correlation. Hurricane days is minus 0.32, and the correlation with the ENSO variation is minus 0.43. Major hurricanes, frequency of major hurricanes, the correlation is minus 0.32, while the correlation is minus 0.39. With major hurricane days, it's minus 0.32. It's comparable with ENSO variations. And this is the accumulated cyclone energy, which is minus 0.3. It's minus 0.4. Now, what does this negative correlation indicate? That means if early onset occurs, there are going to be more major hurricanes. That's what the negative correlation means. So if a later onset occurs in a given season, then there are going to be fewer major hurricanes. Likewise, early onset is likely to lead to more hurricane days, lead to more hurricanes, or more major hurricanes and major hurricanes. And later onset is going to lead to less of these major hurricanes and hurricanes. It does not have as strong of a relationship with the tropical storm. Now, although these correlations are comparable, the CAM onset date has a huge advantage over the ONI index. Because if you recollect, the ONI index is computed over the May through November period. So if you're a forecaster, you cannot use this as a predictor, because the problem is you have to wait till the end of November to get the average ONI index. So CAM onset, on the other hand, occurs in late May or early June, and therefore you can use that as a predictor to forecast with some certainty about hurricanes, frequency of hurricanes, hurricane days, and major hurricanes and major hurricane days. So that's the huge advantage that this predictor has over ENSO variations, despite the fact the correlations of ENSO variations with all these basin-wide tropical cyclone metrics are higher. Now, if we go on the Eastern Pacific side, again, we see the CAM onset correlations are 0.5, 0.44, and note now the correlations are positive. So early onset leads to more tropical, early onset leads to less tropical storms, less storm days, less hurricanes, less hurricane days, less major. So it's opposite influence to what happens in the Caribbean side, which makes sense because, again, early onset has to do with ITCZ, meridional migration and such. So, and I'll be talking about that in a moment, how this onset date is related to tropical cyclone activity and tropical easterly waves in a moment. And in fact, the correlations on the Pacific side of the ENSO index and CAM onset date variations are nearly comparable. So given the fact that this occurs in early May, late June, while this is a contemporaneous correlation, once again, this serves as a very useful predictor for tropical cyclone activity in the East Pacific. Next slide, please. So basically, there are four important ingredients for assessing the tropical cyclone activity in a basin. One is the geopotential, lower tropospheric geopotential height variability. the mid-level relative humidity, which is 700, represented by 700 hectopascal relative humidity, the vertical bulk shear, which is basically 200 to 850 hectopascal vertical shear, and the sea surface temperature. And on the left side, I'm showing you the correlations of May to November oceanic index, NINO index, which is NINO 3.4 index, with corresponding May to November 850 hectopascal geopotential height, 700 hectopascal relative humidity, the vertical shear, and sea surface temperature. And on the right side, I'm showing you the same correlations with the CAM onset date. So early onset of the CAM is associated with this positive correlation with the weakening of the North Atlantic subtropical high, which is basically reducing the northeasterly trades and probably also reducing the shear on the Atlantic side. An increase in mid-level relative humidity across the Central American isthmus and adjacent oceans, and weaker vertical wind shear across the Caribbean Sea, and stronger vertical shear over the tropical Eastern Pacific, and colder SST anomalies out in the Caribbean, while warmer SST anomalies in the Pacific. So these are the large-scale influences that you see with the CAM onset, and likewise with ENSO variations, you see similar variations of mid-level relative humidity, geopotential height, the vertical wind shear, and the sea surface temperatures in the Atlantic as well as in the Pacific. So these are the controlling parameters, and we have gone extensively describing how this affects the tropical easterly wave behavior and tropical cyclogenesis, and why the metrics, the correlations that we showed in the previous slides are a manifestation of these large-scale variations. Next slide, please. So in seasons when La Nina and early onset of the Central American monsoon coincide, the enhancement of the TC activity in the tropical North Atlantic is more likely than other seasons, as the signals from the two sources are likely to reinforce each other. So if you recollect, I had shown you the scatter plot of the ONI index with the CAM onset date, and the correlations were very poor. So our argument is that both the CAM onset date and the ENSO index offer independent sources of predictability on the tropical cyclone activity, both on the Atlantic side as well as on the Pacific side. And therefore, in seasons when La Nina and early onset of the CAM coincide, the enhancement of the TC activity in the tropical North Atlantic is more likely than in other seasons. This stems from similar interconnections that yield weaker NASH, increased mid-level relative humidity, reduced vertical wind shear, and increased TEW activity in the Caribbean region. In the tropical Eastern Pacific, however, the coincidence of El Nino with late onset of CAM is likely to yield an active TC season from warmer in situ SSTs and reduced vertical wind shear. Similarly, our analysis suggests that La Nina and early onset of the CAM is likely to produce a suppressed TC activity in the tropical Eastern Pacific. So there are all these contra indicators, and one has to carefully assess how each of the tropical ocean basins get affected by these large-scale variations. Next slide, please. Okay, so now I'm going to get into the study of onset date variations. There is no standard definition to diagnose the onset and demise of the wet season over Central America. Typically, the start and end date are fixed to a calendar season like June, August, September, or June, July, August, September is considered to be the summer. But there are a variety of methods used in other studies, which include using station data to define rainy pentad thresholds. So that would define the onset of the monsoon. Way back in 1972, Gramzo and Henry made the first comprehensive study of the rainy season of Central America. They use daily rain data from 124 stations in Central America. Start of rainy season was defined as the day when the mean of the daily pentad reaches a threshold of 25 millimeters, and end defined as the last pentad reaching the 25 millimeter threshold. Again, if you look at these definitions, you can define the onset and the end of the rainy season um, only after you have collected the data, and retrospectively you can define it. Operationally, it will be very difficult to define the start and end dates the way they are defined. And then they developed isochrone maps of the evolution of the rainy season. Next slide, please. What we are going to do is use this NASA GPM data set. It is basically a assembly of about a dozen satellites from across the world that have got both microwave sensors as well as IR data that is merged to develop this integrated multi-satellite retrieval for global precipitation. We in fact use version 7, although the slide says version 6. The Global Precipitation Mission was launched in 2014 and was replaced TRIM, the Tropical Rainfall Measuring Mission. But GPM went ahead and retrospectively retrieved using the current algorithm going back to 1998. So now we have, 1997. So from June 1997 to the present, they have produced graded rainfall at 0.1 degree grid spacing. Next slide, please. So before I proceed further, I will also talk about two other phenomena that we see in the Central American domain. One is the Atlantic warm pool, that is the appearance of very warm waters in the Caribbean side, marked by this 28.5 degrees centigrade isotherm. And the area occupied by this 28.5 degree isotherm varies significantly from year to year. In some years, it encompasses a much larger area in the Caribbean and in the Atlantic, while in other times it has occupied a very small area. So that area of the Atlantic warm pool is a pretty significant large-scale climate variability indicator. And likewise, in the East Pacific, there is a warm pool. It's shown in the bottom panel here. And that also marks a significant year-to-year variation and is a good large-scale climate metric. Now, there are some large differences. The Atlantic warm pool is obviously much larger than the Eastern Pacific warm pool. They have a slightly different seasonal cycle. The Atlantic warm pool peaks in early September, while the Eastern Pacific warm pool peaks in early May. Again, you could also define the onset and demise of these warm pools in a similar fashion as I'm going to be defining the onset and demise of the Central American monsoon. And ENSO index is basically averaging the SSTs over the Nino 3.4 region using OISST V2. All right, next slide, please. So the onset and demise of the rainy season is defined as the first day of the year when the daily rain rate falls below the climatological annual mean rate. It's a very simple formula. Unfortunately, the formula doesn't appear very clearly in the next equation, but basically you take the daily and a value of rainfall and subtract the annual mean climatology from it, and you accumulate the daily anomalies, and that is the cumulative anomaly curve. Next slide, please. And so the blue bars are the daily rainfall for a given grid point over Nicaragua for the year 2009 here. And the green curve is the cumulative anomaly curve. So this cumulative anomaly curve shows a very distinct minima and a maxima. The minima marks the onset date, and the maxima marks the demise date or the retreat date of the monsoon. So very objective definition of the onset and demise date. Basically, when you demarcate this onset and demise date, it is basically identifying the onset date is defining the first day when the daily rain rate exceeds the annual mean climatology, and the retreat date or the demise date marks the last day when the daily rain rate is above the annual mean climatological rain rate. So that's how we define the onset and demise date for each of the seasons at each of the grid points. Next slide, please. So this is basically telling us, these arrows are pointing out basically uh, the onset and demise dates and the daily rain rates. Now, the problem is if you are doing this at every grid point, it is quite possible that you will have mesoscale systems that bring in tremendous amount of rain, and that can be mistaken to be part of the annual cycle. So the mesoscale systems could be totally unrelated to the annual cycle, and therefore you need a more robust way of diagnosing the onset dates. So what we do is we generate an ensemble of about 1,000 members of rainfall time series at every grid point. And basically, we randomize the time series by shuffling the time series over a period of time scale of about 6 days, synoptic scale. The idea behind doing this perturbation is basically we are uncertain about the synoptic variations, or the diagnosis of the synoptic variations can affect the onset date. So we generate an ensemble of 1,000 time series at every grid point and generate an ensemble of 1,000 onset and demise dates at every grid point. So if you take an ensemble mean, that would be a more robust estimate of the onset and demise dates rather than taking from the original time series just single onset and demise date. So we are able to generate probabilistically the likelihood of onset and demise date at every grid point. Next slide, please. So when we begin to look at the climatological median onset date from the 1,001 iterations from the 22 years of data that we used from IMERGE, this paper was published a few years ago. So we had used the time period of 2001 to 22. You see a very nice, interesting features. Early onset appears in the southern part of the domain, as well as in the dry corridor of Central America in the northern part of the domain. And in the rest of the Caribbean slope, over Belize and parts of Guatemala, northern Guatemala, you see that the onset is occurring pretty late in the year. So there is a pretty strong gradient, north-south gradient, as well as east-west gradient of the onset dates that you see very clearly. Next slide, please. If you look at the demise date, once again, there's a very strong north-south gradient. The demise occurs much earlier in the northern part of the domain than in the southern part. And in the southern part, the demise occurs much later, probably sometime in early November or mid-November in the southern part in Costa Rica and Panama and along the Caribbean slope, but in the dry corridor that it occurs probably in early October. There is also a west to east progression of the demise date. And if you, next slide, please, that's fine. If you look at the length of the season, you see that there's a very distinct north-south gradient with the Costa Rican region and the Panama region having a much longer season of almost 200 days compared to less than 150 days or ranging from 150 to 170 days in the northern part of the domain. So this is far longer than the traditional calendar month seasons that is often cited in many of the papers. And we are making a case here that the seasonal length of the monsoon season over Central America varies from year to year significantly. Next slide, please. So if you accumulate the seasonal rain over this varying seasonal length, then you see that again there is a very strong north-south gradient with Panama and Costa Rica receiving a large fraction of the seasonal rain in the domain, and the dry corridor is clearly seen with its far less rainfall than over the Pacific slope as well as the Caribbean slope of Nicaragua and Honduras. Next slide, please. If you look at the standard deviation of all these quantities, the onset date can vary from almost a week to 3 weeks. Seasonal length likewise can vary up to a month in some parts of Costa Rica and Panama and even parts of Belize. The retreat rate can also have a large standard deviation ranging from less than a week to almost 3 weeks. And the seasonal rain, as a result of not only the changes in the daily rain rate, but also changes in the length of the season, shows some large standard deviation that range from almost 100 millimeters to 700 millimeters. Next slide, please. Now, the interesting thing is that we can leverage the onset date to provide a seasonal outlook. So if you look at the correlations in panel A at the bottom between onset and demise date, they seem to be largely unrelated to each other. So onset date variations from one year to the other is not related to the demise date relationship from one year to the other. If you look at the onset date and seasonal rain correlations, then you see a large negative correlation, and the white spots that you see, if you see carefully enough, that is basically showing you that the correlations are significant at 1% significance level. And then on the right side, again, panel C, you see the onset date and seasonal length. Again, very strong, significant negative correlations. Basically, these negative correlations with seasonal rain and seasonal length is saying that early onset leads to longer season and more seasonal rain, or late onset in these regions lead to less seasonal rain and a shorter seasonal length. Next slide, please. Likewise, next slide. If we look at the correlations of the demise date and the seasonal rain, we see a positive correlation, but not as significant. But again, it is not exactly overlapping as in the previous slide between onset date and seasonal rain. And the demise date and seasonal length again has very strong positive correlations. And seasonal length and seasonal rain has also got very strong positive correlations. Again, this is telling you, these positive correlations are telling a later demise date leads to a wetter season and a longer season, and early demise date leads to a shorter season and a drier season. Next slide, please. So what we are going to do, and on the other hand, if you look at the ENSO correlations, they are much weaker with the onset date, with the seasonal length and demise date and the seasonal rain. In fact, even though I show statistical significance with respect to t-test, if you do field significance tests, then it fails, and none of these correlations are significant. So in terms of ENSO correlations, they are very weak, and so the variability of ENSO doesn't seem to dictate the variability of the monsoon as strongly as the local onset date variations. Next slide, please. Likewise, if you look at the Atlantic warm pool correlations with all of these four quantities, they are much weaker. They don't affect the teleconnections as strongly. Likewise, the Eastern Pacific warm pool teleconnections are also weak. And so what we are trying to drive the point is that these local onset date correlations are probably one of the most robust ways of describing the year-to-year variations of the Central American monsoon. Next slide, please. Then these are the correlations of the anomalies of seasonal rain with tropical North Atlantic SST. So that seems to have a significant influence on the on the Central American monsoon, which basically is saying that when the tropical Atlantic is warmer, then you would have a wetter season in April and July. The correlation of the anomalies of the seasonal rain with tropical North Atlantic in April and in July with the Central American monsoon onset date, I believe, uh, of the seasonal rain of the Central American monsoon. So basically, it is telling you that the tropical North Atlantic SSTs have some predictive value in April in predicting whether the monsoon over Central America is going to be wetter or drier. Um, so a warmer North tropical Atlantic means weaker northeasterly trades. There is more moisture convergence happening over Central America, and this is likely to lead to more rainfall over Central American region. Next slide, please. So I'm going to not belabor the point, but these are ways to determine probability skill scores, probabilistic skill scores. And I'm using this metric called area under the relative operating characteristic curve. So basically you compute something called the hit rate, miss rate, false alarm rate, and correct rejection rate. And you plot a curve. If you can go to the next slide. You plot a curve between false alarm rate and a hit rate. And if your points are on the upper diagonal above the red line, that's where you say your forecast has skill. So if the area under the curve is greater than 0.5, it represents points on the other side of the red line, and therefore it has skill. If the area under this curve is less than 0.5, it has no skill. That means the forecast is as good as a random forecast. So the green line is obviously a perfect forecast. The purple curve is what typically you see with a forecast that is relatively good, and the bad forecasts fall below the red diagonal line. So next slide, please. So if you use onset date of the Central American monsoon as a predictor of whether the season is going to be wet and short, then you see the probabilistic skill scores. Anytime you see color in this, that means the forecast has skill. So early onset is a good predictor of a longer wet season in most of the domain. You see very strong, very bright colors. The area is almost close to a perfect forecast, 1.0. So if you have early onset in some of these regions in northern part of the domain, the prediction from an early onset that it will be a longer wet season is going to be near perfect. If you go to panel B, the early onset is also a good predictor of wetter wet season, but not as good a predictor for the length of the season. But nonetheless, it does predict reasonably well that the season is going to be wet. Because remember, the wetter season is both a function of the length of the season and the daily rain rate. And early onset cannot dictate the daily rain rate during the season, the intensity of the rainfall. Then if you go to panel C, the late onset is also an excellent predictor of the shorter wet season. And likewise, late onset is also a good predictor in panel D of a drier wet season. So the area under the rock curve, or AROC as we call it here, is significantly high, which is showing you that onset date variations can be a significant predictor for the seasonal rain as well as the seasonal length. So just by monitoring the onset date, you can predict or give an outlook of what the season ahead is going to be. Next slide, please. So the outlook of a better season from early onset has a high AROC, but with more pockets of weaker skill. The outlook of a dry and wet season from the late onset of the season also shows widespread probabilistic skill scores over Central America. Next slide, please. So in conclusion, the Central American monsoon has a complex progression of its seasonal cycle of rainfall. It has these large-scale features of the midsummer drought, the monsoon gyre, the tropical easterly waves that affect it, the local topography also affects it. Local relationships with onset date variations suggest the internal variations dominate the variations of the rainy season. The large-scale variations like ENSO, AWP, North Atlantic SST have limited teleconnections. So these local teleconnections or relationships represent the internal variability of the monsoon system that has an overbearing influence of its year-to-year variations. Across most of Central America, an early or later onset date of the wet season is closely associated with a longer or a shorter and a wetter or a drier season, respectively. These local relationships yield useful seasonal predictability for the Central American rainy season. And the next slide, and all of these material is also available in these papers that I've listed here. Thank you all.
Thanks, Vasu. It's amazing. Complete overview of the Central American monsoon. And now we can check if people have some questions. I received here in the web, there is the chat, some questions. Let me see. Just 1 second. I cannot open here. Can you see in our screen the questions?
Yes, I see the first question.
Can you read and answer, please?
Sure. So one of the question is, can you explain why Central America and Southern Africa monsoons are not considered monsoon areas by IPCC? I think it is, we are still trying to understand and decipher, but I believe one of the reasons why they were limited by not including Central American and South African monsoons is largely because the absence of significant monsoon seasonal reversal of winds, but that is a very weak defense for what they have done, because there are other parts of the monsoons that they seem to recognize that have no seasonal reversal of winds either. So I'm sure that they are going to revisit that point and revise their opinion about monsoon domains.
Thanks. So can you check if there is another question?
I will check.
I think Luis Jesus has one.
Okay, yes. As the ENSO fails to act as predictor for CAM, does the MJO being seen a module teleconnections, or is it too far away? No, MJO does have an impact. In fact, the wet spells of the MJO, I believe phases 1, 2, and 8 produce the monsoon gyre. So the development of the monsoon gyre is very closely associated with the propagation of the MJO. So when the MJO moves towards the Central American region, then you are more likely to see the formation of this Central American monsoon gyre. So MJO is a very critical part, and I did not include that as part of my lecture, which I should have. But the variability of the monsoon or the development of the monsoon gyre is very closely associated with the MJO.
More questions? Thank you, Luis, for your question. Doubts, comments? Okay. Vasu, I thank you a lot for this amazing and complete presentation. It's very useful for us, for our discussions in the panel. And now I will explain some activities for the students. So I will stop the recording. And if you want to stay here, you can stay. And if you need to go, feel free. And
All
thank
right.
you again.
Thank you so much for inviting me. Thank you once
Oh,
again. I'll take the leave. Thanks.
thank you a lot, Vasu.
Bye bye.